Okay, so I'll talk about the test in a second, but first let me give some logistical stuff. Tomorrow I'm not going to be here. Meredith is going to give you a quiz, and then you're just going to spend the time working on assignments. And if you're done with everything, I mean, you can think of it as just like study hall. If you're done with physics, you can go on to other stuff, but I'll give you an assignment so you can get a good chunk of what's due for over the weekend done. And then a week from today is the first lab exam. I started reading your old labs in the reading assignments. I'll do that again for today. So the lab exam Lab exam 1 is based on the first, I think we've had 4 labs. And it'll be basically just answering the kind of questions that were on the labs, doing those things with the directions of the parts of the accelerations and the velocities, position versus time graphs, and answering some general questions about the trends with the air resistance lab. Okay, that one's not going to be in there very much, but a little bit. I mean, the basic answer with the air resistance lab was that for the heights that we were calculating drops from, air resistance didn't make a very big difference. I think there was one case where it did, and that was when you increased the size of the object without increasing the mass, and you dropped it from the high height. But other than that, everything was a very minimal effect of air resistance. Any questions about the first lab exam? All those labs are posted, so if you don't have notes or whatever, you can go back and look at those. Yep. Yes, that's right. Yes, it's going to be individual. You're just going to sit here in class on Thursday and take a test. Yep. And I think the lab exams, God, I'm blanking now. Well, I can look it up. Anybody remember how much the lab exams total are worth? -10. Dang, I got a point right. 20%? Okay. So there are 3 total lab exams, so this exam is worth, 6 2/3% of your grade. And next week, I'll have office hours on, is Monday President's Day?
Yeah.
Ooh, it's my birthday too, 44, if I make it. Okay, so no school on Monday, so no office hours on Monday. I will have office hour on Wednesday. So yeah, if you have questions about the lab exam, maybe make arrangements to come, ask questions, or I can work through problems or whatever on Wednesday. Right? And I think so. Since Monday is President's Day, that means that on Tuesday, where you usually have class with me, you're going to have class with Liam. So you won't see me before the lab exam unless you come to office hours on Wednesday. Yep. At Jefferson. Same, yeah, right. In Meredith's office, normal thing from 3 to 4. Okay. Wow. You will not see me until the lab exam unless you come to that office hour. No, nobody says you have to see me, but if you want to, you have to come to that office hour. That's all I'm trying to say. Okay. And then exam 1. Overall was really good. Median was 50 out of 54, you know. Half the class got 50 or above, and that's great, you know. Most people were in that ballpark, even who were below it. The lowest scores were high for low scores, so really I feel pretty good about everything, but I know there are some people who got lower scores than you would like, and if that happened and you feel like you prepared adequately and then just weren't ready for it, please send me an email or we can talk in person, and I think I can give you some, helpful advice that'll make it go better next time. But overall, I didn't have any concerns about the test. Well, I do have 5 things here that I would like you to think about. These were things that came up. So, like 5 issues that came up, multiple times. The first one is units. I was not very picky about units, but and in this class, I'm pretty lax about asking you to use your units in your calculations. So if you don't have units inside your calculations, that's fine, but you always need to put units on your answers. Okay. The second thing, I just sort of, these aren't in a list of priority. These are just in the list that they started coming up as I was going through exams. But this is really if I had to make one the most important one of this list of 5 things, this is it. Overall, people were not showing enough steps. You don't have to show me a lot, but you need to give me enough stuff that I know what your thought process is. I didn't take off any points for that specifically this time. I'll get more stringent about that as we go on. A lot of people, I think, you've heard this called show your work. And so I think a lot of people don't, because they're like, yeah, my work was in my head. So don't think about it like that. Think about it like you're trying to explain to the grader what your thought process was. You know what I mean? Or what the thought process is that you used. There should be equations on there. And one way that came up is there were people who didn't put anything more than an answer, and then the answer was wrong. And then what am I supposed to do? If you show your steps, I can say like that step was wrong. Here's where you made a mistake with the signs. You get 4 out of 6 on this or whatever. If all you do is put an answer, I have no idea what you did right, what you did wrong. I just know that the answer isn't right, So there's kind of 2 parts to this. One is to maximize partial credit, and the other one is just the person grading it wants to know that you know an appropriate set of steps for how to do these problems. And then the third one was in the problem where you had to calculate an initial position and a final velocity in terms of a couple of variables, and one of them was g. G is equal to positive 9.81 meters per second squared. And so I think a lot of people were thinking of it as negative 9.81, and so then the signs were backwards on that problem. It wasn't a big problem. I didn't take off a lot of points, but what that means is your acceleration vector in free fall problems is actually 0, negative g. Okay. Think of g as the magnitude of the acceleration due to gravity, and then the positive or the negative are part of the direction, you know. So you have to provide the direction because you're choosing what the coordinate system is. The fourth one came up on that same problem where you're trying to calculate the initial position and the final velocity in terms of a few variables. It was a problem where something was dropped, I think from a bridge or something. And a lot of people in their answer had V0 in there. V0 in that problem, because it was dropped from a bridge, was 0. So you didn't need that in there. So when something is dropped, its initial velocity is the velocity of what it's dropped from. Okay, so if something's dropped from a bridge, hopefully, if it's a good quality bridge, that means the velocity of the thing when it's released is 0. Okay? If something's dropped from a car going 200 miles an hour, at the instant the thing is released, it has a velocity of 200 miles an hour in the direction the car is going. Okay? So if something's dropped from the vehicle, that initial velocity is the velocity of the vehicle. If it's dropped from the ground or a bridge or a building or whatever, the initial velocity is 0. And then the last one was relative motion. I asked you to give the appropriate relative motion equation. And it should have been like this. We were doing acceleration on the test, right? Mm-hmm. Okay, so it should have been acceleration of the object relative to the ground is equal to the acceleration of the object relative to the elevator plus the acceleration of the elevator relative to the ground. What I saw, at least a handful of times was acceleration of the object relative to the elevator is equal to acceleration of the object relative to the ground plus the acceleration of the ground relative to the elevator. Technically that's right, but that's not a good way to think about this. And the reason it's not a good way to think about it is this term makes physical sense. This term makes physical sense, but this one is hard to wrap your head around. What's the acceleration measured by the ground based on the camera in the elevator? It does have a meaning, but that meaning is confusing. So think about it as like you're always starting with the position, velocity, acceleration of the small thing relative to the overall, the biggest outside view. And then you're going in from there. It does turn out, by the way, that you can do this if you recognize that the acceleration of the ground relative to the elevator is always, the acceleration of one thing relative to another thing is always negative of the other thing relative to the, you know what I mean, like that. If you switch the order of the two subscripts, you switch the sign. I took points off for that. If you, even though mathematically it makes sense, if anybody feels really, really strongly about their understanding of that and that they, you know, whatever, you want to argue it to me, I'm open to that argument. I took the points off because this is a better way to think about it, I think. But any questions about any of those 5 things? If you looked at your test and looked at that list of 5 things and took to heart those 5 things, I would be very happy with the good that came out of taking this test. You know, those are, I think, all 5 of those things are important things going forward. Anybody have any questions about the test or want to see how you do any of the problems or anything like that? Yep. Yeah. Oh, okay, yeah. Let's do the relative velocity one. So that's the one, the accelerator, the elevator. So you have an object that's being dropped. The elevator is accelerating up at 2 meters per second squared. The relative motion equation for this is elevator's going down, right? Okay, so the acceleration of the ball or the object relative to the ground is equal to the acceleration of the object relative to the elevator plus the acceleration of the elevator relative to the ground. And so we know that something in free fall, anything in free fall, if there's no air resistance, no important air resistance, then its acceleration relative to the ground is 0, negative 9.81. We're trying to calculate the acceleration of the object relative to the elevator. And the acceleration of the elevator relative to the ground is down at 2 meters per second squared, so 0, negative 2. And so just do the algebra and you get that the acceleration of the object relative to the elevator is equal to 0, negative 2, nope, 0, negative 9.81 minus 0, negative 2. So that's 0, negative 7.81 meters per second squared. So it's still accelerating down. You know, to an observer in the elevator, it still appears to accelerate down, just not as much as you're used to seeing something accelerate down when you drop it. Any other questions about the test? So like I said, overall, I was really happy. I don't think anyone should feel freaked out about the test, but if you want to talk to me about how to be a little more ready for the next one, I'd be happy to do that. Okay, so last time we started talking about, so back to particle kinetics. And the big story in particle kinetics is Newton's second law that says the net force acting on an object is equal to the mass of the object times the acceleration of the object's center of mass. So where F net is the sum of all forces acting on the chosen object, M is the mass of the chosen object, and ACOM is the acceleration of the chosen object's center of mass. This idea of the chosen object is something we're going to have to be very careful about. It comes in all of those, and we're going to have some tools to be very clear to ourselves about what the system is that we're isolating, what the object is that we're isolating. Okay, I'm going to do one more example where we calculate the net force. We did one of those last time. And then we'll go on to the next topics. So let's say that there's a ball on a string that's traveling around in a circular path. So let's say it takes 2 seconds per revolution. And the circular path has a radius of 10 centimeters. And if this is our coordinate system, X, Y, Z pointing that way, we want to calculate first, what's the direction of the net force at the instant shown? And then second, what are the vector components of F net? It doesn't say this really explicitly, but the idea here is that this is moving at a constant speed. What's that called? Circular motion with a constant speed? Uniform circular motion, yep. Okay, so if you're thinking about this from above, then here's the object, here's the center, it's rotating this way. What's the direction of the velocity vector?
Right.
Up, that's right. It's tangent to the path in the direction of motion. What's the direction of the tangential acceleration? Tangential acceleration is the one that's parallel to v, and so there's none. It's moving with a constant speed, And so if the speed isn't increasing or decreasing, there's no parallel part. And then what's the direction of the centripetal? Yep. So there's the centripetal acceleration. And since there's no tangential acceleration, this is also the total acceleration direction. Okay, so the total acceleration is right towards the center. I'll draw it like this. And so if we know the direction of the acceleration is towards the center, what do we know about the direction of the net force from this equation? If you multiply a vector, acceleration of the center of mass here, by a constant, a positive number, what do you get for direction? What does that positive number do to the direction of that vector when you multiply? Same direction. Everyone's like, I know it, but I'm embarrassed for you to even ask. So F net always has to be in the same direction as the acceleration of the center of mass. Okay? Always, because M is always positive. So anyways, the idea is this is also the direction of F net. So now let's calculate the components. Oh, and I need to give a mass. Let's pretend I did that before. The mass is 50 grams. Okay, well, we know the, so we're going to use Newton's second law. We know the net force is going to be equal to the mass times the acceleration of the center of mass. That's the mass times the acceleration of this particle. How do we calculate the components of the acceleration? We're going to use the circular motion idea. So the tangential acceleration is 0, 0, 0. Right? We know it's not speeding up or slowing down. The centripetal acceleration is omega r acting toward the center. So if we know omega and we know r, we can figure out the components of this vector. R is 10 centimeters, which is, what's that in meters, 10 centimeters? 0.1, yeah. And how are we going to figure out the angular velocity? We know that it takes 2 seconds per revolution. So we know that it's 2 seconds for every 2 pi radians. And so that's 1 over pi seconds per radian. And so the reciprocal of that just says pi radians per second. Are you with me on the reasoning on that? And so the centripetal acceleration is equal to pi times 0.1 toward the center. And that is 0.1 pi in the negative x direction. So that's negative 0.1 pi 0. I guess we're doing this in 3D, so I'll include a z component. And that's meters per second squared. And so Newton's second law says F net is equal to the mass. In SI units, what's 50 grams?
You mean, so per kilogram?
Yeah, in kilograms.
0.05.
Good. So the mass is 0.05 kilograms times the acceleration vector of negative 0.1 pi 0, 0. And so you get negative 0.005 pi 0, 0. And what are the units? Kilogram meters per second squared, which is newtons. Yep. Newtons are the units of force in SI units. Any questions about that one? Well, we're not always going to want to calculate F net. Usually we're not. Usually we're going to want to calculate individual forces. How hard is, like, for example, what's the tension in this string, you know? And so we need a couple of other tools in order to calculate that. What we know in this case is that F net is equal to the sum of the force of gravity plus the force applied by that string. And we're going to want to be able to break it up into those pieces. So that's what we're going to go into next. So now we want to break up net force into individual forces. That requires two things. The first one is a representation called a free body diagram. I'll always abbreviate that FBD. And a free body diagram is, well, it shows all the individual forces acting on a body. On a chosen body. And then the second thing that we need to figure out is how to represent these individual forces. Or let's say how individual forces act. And we're going to talk about 5 different types of individual forces. Okay, so the first thing I'm going to talk about is free body diagrams. the free body in free body diagrams means that we don't show anything except the body we're isolating. Anything but the chosen body. And the surroundings are only represented by the forces they apply. I guess the forces they apply to the chosen body. And okay, so draw closed outline of the body you're isolating. The chosen body. With no internal details and no external objects. So here's an example. Let's say you have a car and someone pushing on the car. And a helicopter pulling on the person. And let's say on the roof there's like a pig. It's a very stylized helicopter. You can, I can teach you. Okay, so let's see. What am I drawing? A pig? Oh yeah, well, these are nostrils. Okay, and then the car is on the ground. Okay, so a free body diagram, if you're drawing a free body diagram of the car, so if the car is the chosen object, then closed outline looks like that. Okay, so there's no internal details. I didn't draw the windows. I didn't draw the wheels as separate things from the car. I'm just trying to be really clear to myself about what the boundary is between my chosen thing and the outside world. Okay, that's the whole point of this free body diagram. It helps you be clear to yourself about the boundary between your chosen thing and the rest of the stuff. And I didn't draw any of the other crazy stuff going on because those are external objects. Okay. Then represent all the forces applied to the chosen object by the outside world as force vectors. And that means that you're going to draw an arrow in the direction of the force. And it's going to be associated with a scalar value, a number, or a scalar variable. Okay, so in this example, there's like a million things going on in that picture, right? So how do you know when you've represented all of the forces that the outside world is applying to this thing? So how do you know when you've represented all the forces? Well, forces are only going to appear in two ways. The first one is called field forces. Those are forces created by force fields, and force fields aren't as cool as they look in like Super Friends or something. Force field just means that no matter what path you take to get to a location, once you're at that location, the force applied is specified. So gravity is a force field. Magnetic forces are force fields. Electrical charge forces are force fields. So gravity, magnetic fields, electric fields. For us, it's pretty much as always going to be gravity that we're talking about. In that problem above, there's no reason to think that there's any important magnetic forces or electric forces, so we're just going to deal with the weight. And then once you've put the weight force in there, the only other type of forces are contact forces. Outside world touches the boundary. Okay, so in this example, First, we're going to deal with the force that gravity applies to this car. That's just going to be a downward force of the mass of the car times g. And now all we have to do is mentally go around the boundary and look for places where the outside world makes contact. So I'll start at the front wheel. There's a contact between the ground and the front wheel. And we haven't talked yet about how to know the directions of these forces, but there's one there. I'll call that N front for normal force. The way I'm representing these will make more sense by the end of class today. But for now, all you have to think of is, yeah, there's contact at the front wheel, so there has to be something there, okay? And then where's the next, if I keep going around counterclockwise, where's the next place that there's contact with the outside world?
The man.
Yep, so I'll call that R for reaction, man. And keep going around the boundary, where's the next place?
Pig sitting on top.
Yep, the pig, that's this way, call that F pig. And then keep going around, and where's the next place?
No second.
The windows are part of what's included in our free body. So we don't have to represent those. Those are inside the boundary. So the next place the outside world contacts is at the back wheel. I'll call that N back. And now we're done. We've treated the only field force, gravity, and then we've gone all the way around the boundary and put a force where that represents every place that the outside world makes contact with the chosen body. So what about what is not shown in here? Notice that there's no force representing the helicopter, okay? And at first you might think like, well, that's got to be in here because the force applied by that man would be different if that helicopter wasn't there, right? Somehow that has to be represented. But it doesn't show up here, and it doesn't show up in Newton's second law for the car. If we did a free body diagram of the man, there'd be a force of the car pushing on him. There'd also be a force applied by the helicopter. But all we're doing is just going around the boundary and looking for what's in contact with that boundary. If it's not in contact with the boundary of your chosen body, it doesn't show up in the free body diagram, and so it doesn't show up in Newton's second law. Okay? So no helicopter. I really only put it in there because I'm so awesome at drawing helicopters. Okay, so the next thing we have to do, anybody have any questions about free body diagrams? So the next step is to figure out what direction individual force types are going to apply. Next step. Figure out the directions of the individual forces. And there are going to be 5 types that we're going to deal with. The weight, that's the force applied by gravity. Okay, that's the easy one. Second is pushing contact. third is pulling contact. That's usually going to be with cables. And cables include, ropes and strings and anything. So a cable is something that you can't use to push on something. Okay? A string, you can't use it to push on something. All you can do is pull it towards you. Fourth is friction. And the fifth one is the force applied by springs. That seems like sort of a random one, I'll bet. Because, like springs are not normally like a real important part of your everyday life, the way pushing and pulling and friction are. The reason that spring forces are mentioned, the reason we deal with those in Physics 1, is because actually this idea of how springs apply forces is the lead-in to a whole important area of engineering. Any kind of elastic body, which, like engineering materials, like for example with engineering materials, if you have a block of steel, if you apply big forces to it, it deforms a little bit. You can't see it. You can't see how much it deforms, but it does deform a little bit. And there's a linear relationship between how much it deforms and how much force you apply. And that's the same relationship that springs have with the forces you apply. And so it's sort of a lead-in to this branch of engineering that's really important in, engineering firms use this idea all the time. So, yeah, I think it seems it's like, oh, well, what about the force applied by like staples or like paper clips or something? Like spring seems sort of like a weird idea, but that's why we're doing it. Elasticity. You know the word elasticity? Like elastic. What does elastic mean to you? Yeah, it means stretchy, mainly in your, like, I think that's how most people have it stored in their head. What it really means in physics isn't the stretchiness, it's that when you let go, it returns. Okay? So, like, Play-Doh can stretch, but then when you let go of it, it's still in the shape you stretched it to, you know? Something that's elastic, you stretch it, but as soon as the force is gone, the thing's back to its original shape. And that's the idea of springs and engineering materials like steel and so the first one we're going to do is pushing contact between two bodies. Pushing contact force. So when two bodies push against each other, the force applied to the chosen object, so when you're dealing with this force, you're just going to be isolating one of those two objects that's pushing. That force is perpendicular to the surface of contact toward the chosen body and away from the contacting body. Okay, so let's think about, for example, two balls that are in contact. Let's call this one body 1 and this one body 2. And I'm going to draw free body diagrams of 1 and 2. So free body diagram body 1, we're just drawing the outline. You know what? I skipped the weight. Dang it. Well, anyways, make this number 2. Pushing contact force is number 2. Well, how much do I really have to say about the weight? I guess anyways. The weight is always down, and the force is... I do have to talk about that. Oh! Okay, we'll do 2 first and come back to 1. It's just, yeah, we'll come back to 1. It'll be okay. No, we have to. Okay. Scribble that out for now. All right, we'll come back to it. I'm going to save it because I'm lazy. I'm going to save it and just copy it in later. Just do that in your notebook. No, I know that's cheating. I shouldn't do that, but I just can't throw it all away. I can't. Okay, the first one is weight. So what's the force that an object's weight applies to it? So gravity always applies a downward force that's proportional to the object's mass. So how can we figure out what that is? So how can we figure out what that force is? Well, if we think about an object that's in free fall, we know what its acceleration is. We've measured that. And we know that the only force acting on it is the weight. So think of an object in free fall. The only force is the weight. And the acceleration is g down. Okay. So we're going to use Newton's law to figure out what Newton's second law to figure out the force. So let's say we have an object in free fall with a mass m. The free body diagram, nope. Let's just go straight to Newton's second law. The only force is the force of gravity. I'll write that as this force vector applied by gravity. That's our F net in this case. That's equal to the mass of the chosen object times the acceleration of the chosen object, which is mass times 0 negative g. So the force vector applied by gravity is 0 negative mg. So the weight force on any object of mass m is mg down. That can seem a little strange at first because, we've done these whole labs based on the idea that no matter, and all of the 2D kinematics free fall stuff we did was based on the idea that something's in free fall, no matter what its mass is, falls the same, And now we find out that things with different masses have different forces applied to them by gravity, But Newton's second law says that if you have a bigger mass and it's accelerating the same amount, it has to have a bigger force applied to it. So it's kind of a strange thing, but gravity applies more force to big things, less force to small things, and the effect of that when they're in free fall is that they both fall with the same acceleration. Okay? So for example, the free body diagram for an object in free fall. So this is a body in free fall. This body isn't in very good shape. The force is mg down. Okay, so what's the force applied? So we know the force applied by gravity if something's in free fall. You're just going to have to take my word for it that that the force applied by gravity, if something isn't in free fall, is that too. Gravity pulls just as hard on objects, whether they're rolling, sitting there, in the middle of a collision, in free fall, whatever. Gravity's always pulling equally hard on something with a given mass. Okay. Okay, so now insert your little pushing contact force thing that you saved. Okay, so let's see. Pushing contact force. This is the second one. When two bodies push against each other, the force applied to the chosen body, remember that chosen body is always a big deal with these, is perpendicular to the surface of contact toward the chosen body, away from the contacting body. Okay, so as an example, this might look familiar. So say you have these two balls that are in contact with each other and they're both sitting on a table. And I'm going to draw free body diagrams of both of them. So the free body diagram of body 1 So we just have the outline of the body. There's a weight force that's equal to the mass of the first ball times 9.81 meters per second squared down. And then where are objects pushing on this ball? Go around the boundary. It's pushing on it.
The table.
The table, yep. So that's a force up, and I'll call that N for normal force. So how did I know that it was up? That pushing force is perpendicular to the surface of contact toward the chosen body away from the contacting body. So this is, can you not do that? This is, the surface of contact is the floor, the ground. The chosen body is the ball, so it's towards the ball, away from the ground. Okay? And where's the other pushing contact?
Ball number 2.
Applied by the ball to. Perpendicular to the surface of contact means either to the left or the right. And toward the chosen body, away from the contacting body means like that. And I'll call that R. Any questions about that? Okay, and then free body diagram of the second one. There's the weight. I'll call that M2G. And then there's a pushing, let me change this where I called this the normal force. Let's call that N1 because there's going to be a different normal force for the second ball. There's a pushing contact from the ground onto the ball. We'll call that N2. That's perpendicular to the ground, toward the chosen body, away from the ground. And then there's a pushing contact from ball 1. That's perpendicular to the surface of contact, toward the chosen body, which is now the other ball, away from ball 1. So this time it's that way. And I could call that R2. We're going to see pretty soon that those two forces have to be the same. That's Newton's third law. If you've ever heard the phrase, for every action, there's an equal and opposite reaction, that's what that means in mathematical terms. Those magnitudes have to be the same. Okay, so let's go back to the car with the pig and the helicopter. And okay, so in this example, if we're isolating the car, what things are pushing on the car? The man is definitely pushing. The pig is definitely pushing down. And then the ground. So all 4 of those forces that we applied to this car are pushing contacts. So let's look at the free body diagram. And all of these, both of these 2 forces applied by the ground are perpendicular to the ground, toward the car, away from the ground. The force from the man is perpendicular to the surface, toward the car, away from the man. And the force applied by the pig is perpendicular toward the car, away from the pig. And so, you can have pushing contacts on this one object that are in all these different directions because of where the contacting body is and because of the shape of the surface at the point where that pushing happens. Any questions about that? So let's do an example problem. There are a lot of problems that you can do with only weight and pushing forces. So let's say that we have two carts in contact. Let's say this one's 5 kilograms and this one's 3 kilograms. And let's say you apply a 40 Newton force to the left of the 5 kilogram box. So the first question is, what's the acceleration of the system? And the second question is, what's the force vector on the 5 kilogram box cart by the 3 kilogram? You could imagine that this actually kind of question is a really important concern if you're doing engineering calculations. Like if for some reason you have a system where this is going to be happening, you want to know what forces these are going to apply to each other so you know what kind of materials you have to use, how thick that surface has to be, things like that. Okay. Okay, so to calculate the acceleration of the system, whenever you need to calculate the acceleration of a system like this, the first thing you want to do is isolate both of the two things together, or all of the things together. Okay, so first I'm going to do a free body diagram of both. Okay, so here's an outline. And what forces are acting on this?
40 newtons.
Yep, 40 times 9.81 is 390, 392.4, I think. 39.24. No, wait, scratch that. The weight is the mass times 9.81. So we have a total mass of 8 kilograms times 9.81. So that's 78.48 newtons down. And now we're going to go around the boundary. Yep, there's a force over here. I'll call that N3. Keep going around. Now, what about the contact between those two?
Doesn't count.
That doesn't count because that's not the outside world acting at the boundary. That's happening inside the boundary, and we don't care about. We keep that, that's a family issue. We don't worry about that. And then keep going around, and there's the 40 newtons. And then there's another contact over here, the normal on the 5. Okay, so now we're going to use this in Newton's second law. And the benefit of the free body diagram, especially as systems get more complicated, is you have a representation of everything that goes into the left side of Newton's second law. So in vector form, that 40 is in the positive x direction. N5 is in the positive y direction. 78.48 is in the negative y direction. N3 is positive y. And all that's equal to the mass of the system. What's the mass of our chosen body?
8.
8. Yep. Times the acceleration. And now, do we know anything about the acceleration of this system?
No.
Well, we're going to assume one thing about it. We're going to assume that since it's on a horizontal ground, all it can do is move this way or that way. It's not going to jump up into the air or sink into the ground. And so we're going to assume that there's only an x component to the acceleration. Okay. So the acceleration is just going to be a0. So what we're doing here is assuming all motion is parallel to the ground. Or to the surface. Okay, so this gives two equations. The first one says 40 plus 0 plus 0 plus 0 is equal to 8a. And the second one says n5 minus 78.48 plus n3 is equal to 0. If we're just trying to calculate the acceleration, this one doesn't help us. And this one by itself gives us the answer. So this variable a is equal to 5 meters per second squared. And then how do we go from that variable value to our acceleration vector? Well, remember, we've already represented the acceleration vector here. Right? That's the acceleration vector. So now that's it. We just didn't know what a was. Now we know what a was, so we can plug it back in there. So we'll plug this variable a back into the acceleration vector, and we get the acceleration vector is equal to 50 meters per second squared. Any questions about that? Okay, so that's the first time that we've taken information about causes of motion, mass and force, and use that to calculate what the motion is. The motion is going to result from that. Now we want to figure out the force vector on the 5 kilogram box by the 3 kilogram. So we're going to isolate the 5 kilogram box. So for part B, we're going to draw a free body diagram of the 5 kilogram box. So there's the outline. What's the first force to put in here? The weight.
Times.
Yep. So now our chosen body is only the 5 kilogram box. So this is 5 times 9.81, so 49.05. And now, I don't know why I always seem to start with the right bottom, but starting over here, there's a contact with the ground. That's a pushing contact, so it's perpendicular to the ground, toward the cart, away from the ground. I'll call that N5. And then there's a pushing contact from the 3 kilogram box. That has to be pointing to the left. We'll call that R. And then nothing, 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 nothing until we get to the left side. And then we have that 40 Newton force applied to the outside. Now Newton's second law. Yep.
I was just wondering why we didn't use for the other wheel.
I'm lumping them both into one force. I guess I just did that because if we were asked specifically for the forces on the individual wheels, you would break it up. But actually, now that I think about it, we're still dealing with everything as a particle. Really, we're not making any distinction yet about where things, because remember, particles don't have any length dimensions. And so really, we're assuming all this stuff is happening at the same place. So two forces happening at the same place by the same object, we'll just call it one thing. Okay, so Newton's second law says 40, 0, plus 0, negative 49.05, plus 0, n5, plus, now this R force is pointing in the negative x direction, so that's negative R, 0, is equal to the mass of the chosen object times its acceleration, and we know that acceleration vector is 5, 0. Both of these two things have the same acceleration. So the first equation says 40 minus R is equal to 25. The second equation says negative 49.05 plus N5 is equal to 0. So again, with what we're asked, this one doesn't help. We can get everything we need from this. Question? Oh, yeah. Well, it's a vector equation, right? And you can always break up vector equations into an x equation and a y equation. So think of this whole vector equation is two equations. 40 plus 0 minus r is equal to 25. And 0 minus 49.05 plus n5 plus 0 is equal to 0. Okay.
Oh, okay, wait, never mind. I just
Okay.
answered my own question.
And so now solve for r, and r is equal to 15 newtons. Okay, well, we want the force vector applied to the, this is just a scalar variable. We want the force vector applied to the 5 kilogram by the 3 kilogram. So how do we go from this to the vector? The answer is pretty much the same as we did with the acceleration. This thing here is the force on the 5 by the 3. We just didn't know yet what r is. Now that we do, we can plug it back in. So plug in r, and you get that the force on 5 by 3 is equal to negative 15, 0. So what we figured out there is, if you have these two objects with those masses, and you apply a 40 Newton force to here, the contact force between these two is going to be 15 newtons. I mean, you look at that and have no idea. I mean, there's nothing intuitive about that answer. You could never just look at it and guess, but we can calculate that. Any questions about that? Okay, here's another one. So let's say you have sort of a carousel thing. And there's a box sitting on the carousel. And this kid is sitting here holding this box on the carousel. The kid's pushing on the, okay. Can you follow what I'm trying to get at here?
Yeah.
Okay. And the distance between this and the center is 1 meter. The carousel has an angular velocity of 5 radians per second. And no angular acceleration. And the mass of the box is 10 kilograms. What's the force vector that the kid applies to the box? Okay, we're assuming that there's no friction between the box and the carousel. And we'll use a coordinate system like this, where that's x, that's y. Okay, so the first thing we have to do is figure out the acceleration of the box. So I'm going to draw it from a top view. The box is in circular motion like this. The velocity is this direction. The centripetal acceleration is this direction. What's the tangential acceleration direction? 0, because there's no angular acceleration. So tangential acceleration is 0. The centripetal acceleration is omega squared r, acting towards the center. So that is 5 squared times 1, or 25 meters per second squared this way. And in components, that's the negative x direction, so that's negative 25, 0. Any questions yet? Okay, so the total acceleration then is equal to the centripetal acceleration because the tangential acceleration is 0. So the total acceleration is negative 25, 0. Now we'll draw a free body diagram of the box. And we're going to do this in a top view. Okay, so what forces are acting? There's a weight, the kid. So I'm going to just always put the weight. So the box has a mass of 10 kilograms times 9.81. What direction, if this is a top-down view, what direction is that acting? It's like into the page. So I'm just going to leave that out because it's out of the plane of our coordinate system. And what about the pushing force from the carousel up onto the box? What direction is that? That's out of the page. That's also out of our plane. I'm going to leave that out too. So the weight and the normal force are out of the plane. And then there's the force applied by the kid, which is this way. That's a pushing force, so it's perpendicular to the surface, toward the chosen body, away from the contacting body. I'll call that R. Okay, so now Newton's second law says the force, this is the only force acting on it in our plane, negative R, 0, is equal to the mass of the chosen body times the acceleration of the box, which was negative 25, 0. We get two equations. The first one says negative R is equal to negative 250. The second one says 0 equals 0, so that doesn't tell you anything. But this first one says that R is equal to 250 newtons. The force vector the kid applies to the box is this. So plug R into that vector, and you get that the force on the box by the kid is equal to negative 250, 0. Any questions about that? Okay, so you'll start tomorrow. You know, Meredith's going to be there. I'm not going to be there. You'll start with a quiz, and then you can just work on the assignment. Yeah. So have a good weekend.